Welcome back. Today's topic, we're going to be looking at matrices. That's the plural of the word matrix. It's going to seem a little disjoint from the systems that we've been working on for a couple of days, but hopefully tomorrow I'll be able to show you the connection between the two. Now, keep in mind this is a unit of additional topics, so there will be some disjoint concepts that we're going to look at, but the first few sections here are definitely related. Okay, so I don't know if you've seen a matrix before. Not the movie Matrix, but a matrix in math. It's basically just a rectangular array of numbers, just a way to arrange our numbers. So in a rectangular array of numbers that we call a matrix, we have the entries or elements of the matrix, the numbers that go inside. Okay, so the array of numbers or the numbers inside, we call its elements, or we could also call them entries. Okay, and your matrix, your rectangular array, is named by the number of rows that it contains, followed by the number of columns that it contains. So when you are trying to establish the dimensions or the size of your matrix, it's rows by columns. And in case you're not sure on the difference, rows are horizontal. Rows are horizontal, so left and right. And then columns are vertical. So the columns are the ones that are up and down. So I like to remember because that L is looks like a vertical line in the word columns. That's how I remember that the columns are vertical. Okay, so when we're looking at the first example there, that is an example of a matrix. It's got 6 entries or 6 elements, and we would call it a 2 by 3 matrix because it has a row here and a row here. It's got 2 rows and then 3 columns, a column here, and a column here. So a 2 by 3 matrix because it has 2 rows followed by 3 columns. Okay, so the first thing we're going to look at is actually pretty straightforward. Basically order of operations, adding, subtracting, multiplying. When we're looking at matrices, if we have a number outside of a matrix, it's sort of like having a number outside of a set of parentheses. It's intended to be distributed or multiplied to all of the entries in the matrix. So we call it a scalar. Okay, and it gets distributed or multiplied into each of the entries or elements in the matrix. And 2 matrices can only be added or subtracted if they have the same dimensions, which would make sense. You wouldn't be able to add matrices if they didn't have elements that corresponded. So first row, first column, element in one matrix versus the first row and first column of the other, where if you had a spot in one that didn't correspond with another, there's no way that you could add or subtract. Okay, so if we're looking at scalar multiplication, addition, and subtraction, we have to make sure that multiplication happens before any addition or subtraction. That way we're following our order of operations. Okay, so we're going to use these 3 matrices just to run through a few examples here. So if we wanted to find 3C, that literally means to multiply 3 by each of the entries in matrix C. So C has 1, -4, 8, 1/3, -2, and 0. We took each of these entries and distributed in that 3. Multiply by 3, multiply by 3, multiply by 3. And again here, and here, and here. We're going to end up with a new matrix. So 3 times 1 is 3. 3 times 8 is 24. 3 times -2 makes a -6. 3 times -4 is -12. 3 times a third, or a third of 3, so it's going to be 1. And then 3 times 0 is 0. Okay, so simple as that. If we're multiplying by a scalar, it's just distribution. It's just multiplication by each of the elements. Okay, now if we have a multiplication and subtraction, as we have in number 2, we have to make sure that we do the multiplication first. So we are looking at 2 times a in this one. So 2 times a would be 2 times 2, 0, 1, and 4. We're going to figure that out before we subtract b, which is the 3, -1, 5, and 2. And you could take a couple of steps to do this, but I'm going to try to knock this out in a little bit more efficient of a manner here. So if I multiplied here first, 2 times 2 would be 4. Then we're going to subtract the corresponding element there. So 2 times, oops, I'm not sure how the calculator popped in. 2 times 2 is 4, minus the 3 in that corresponding spot would give us an entry of 1 here. And then, let's see, change colors. 2 times 1 minus the 5 that's here So 2 times 1 would be 1 minus the 5. Sorry, 2 times 1 would be 2. 2 minus the 5 would be a negative 3 in that spot. And then we're going to go here, 2 times 0, and then we're going to subtract the negative 1. So 2 times 0 is 0. 0 minus a negative 1 would be 0 plus 1, and 0 plus 1 is just 1. And then lastly, we have 2 times 4, which would be 8, minus the 2 here would give us 6 in that spot. Okay, so there would be the matrix resulting from 2 times A minus B. Okay, B minus C, if you notice, B is a 2 by 2 matrix. So we have 3, negative 1, 5, and 2. And if we tried to subtract C, which is 1, negative 4, 8 and 1/3, negative 2 and 0, we're not going to be able to perform this operation because while we have entries that correspond here, we have entries that correspond here, we have nothing to correspond with the elements that are in this last column. So this is not possible. And that's all we would have to say for an answer. Okay, it's not possible to multiply. Now, I only wrote that out for the purposes of your notes. If you're looking at them, you can see they're not the same size. You know that that's not something that can be done. Just simply writing the answer not possible is going to be fine. Okay? All right, last one. Feel free to pause if you wanted to try to work this out and then come back and see how you did. We're looking at B, which is 3, negative 1, 5, 2. And we want to subtract 3 times A, which is 2, 0, 1, and 4. So we're looking at, again, corresponding entries here. So we have 3 in this first matrix, and then we're going to subtract 3 times 2, which is 6. So the 3 minus the 6 is going to give us a negative 3. And then we're looking at 5 here, and we're subtracting 3 times 1. So we're subtracting 3, and 5 minus 3 gives us a 2 in that next entry. And then we have negative 1 here, minus 3 times 0. Well, 3 times 0 is 0, so negative 1 minus the 0. So we're going to leave us with negative 1. And then lastly, we have 2 here, minus 3 times 4. So 3 times 4 is 12. If I have 2 minus the 12, 2 minus 12 is going to give me a negative 10 in that last entry. Okay? So hopefully that's pretty straightforward. That's just scalar multiplication, so distributing in a factor, and then possibly having to add or subtract corresponding entries. And then again, if we don't have corresponding entries or our matrices aren't the same size, we wouldn't be able to add or subtract. Now, multiplying not by a scalar, but actually multiplying matrices is a little bit more challenging. In fact, you can only multiply 2 matrices if the number of columns in the first matrix is equal to the number of rows in the second. And then when we multiply, the product is going to contain the number of rows from the first and the number of columns from the second, which is kind of a complicated thing there. And I will show you when we get to number 6 and 7. If you look at number 6 and 7 real quick, we have the same 2 matrices, but the order is rearranged. And what we're going to see when we get there is that the order matters. Since the order matters, we would say that multiplication is not commutative, like normal addition or multiplication. Sorry, I can't spell. Normal multiplication is commutative. If you multiply 5 times 4 or 4 times 5, it doesn't matter which way you multiply that, you get 20. We call that the commutative property. That does not apply to matrices. Okay, multiplication is not commutative, is the word I was trying to write before. Okay, so in order to multiply 2 matrices, we have to look at the number of rows and columns in each of our matrices. So looking at number 4, the first matrix, remember it's rows by columns when we name it. So we would say that this has 1 row and it has 3 columns. So we would call it a 1 by 3 matrix. If we look at the second, it has 3 rows and it has 1 column. So the second matrix is a 3 by 1 matrix. Now, according to the rules of multiplication with matrices, the number of columns in the first has to equal or match the number of rows in the second. So I need the number here of columns and the number here of rows. Those numbers have to be the same. So these numbers need to be equal. And if they are, then our product, sorry, let me move this. If they are, then when we multiply, our product is going to contain the number of rows. Now I have my lasso on. Sorry, I messed this all up. The answer is going to contain the number of rows from the first and the number of columns from the second. So this is going to be the size or the dimensions for our answer, for our product. Okay, so because there are 3 columns and 3 rows, 3 columns in the first, 3 rows in the second, those numbers match, we can actually multiply these matrices, and then our answer is going to have the number of rows from the first and columns from the second. So our answer is going to be a 1 by 1 matrix. 1 by 1 means we're only looking at a single entry. So now the question is, what goes in that single entry? So when we multiply, I'm probably going to have to make this a little bit bigger. When we multiply, what we are doing is multiplying this row by this column by multiplying the first and first number, second and second number, third and third number, and adding those results together. So we're multiplying the 1 and 4, so 1 times 4, plus we're going to be multiplying the 2 and 5, and then lastly, again, I made this too small, and lastly, we're going to be multiplying the 3 and 6. And if we find the sum of those products, we have the result for our 1 entry matrix. So the 1 plus 4, or 1 times 4 is 4, 2 times 5 is 10, and 3 times 6 is 18. If we add 4 and 10, we have 14. 14 plus the 18 gives us 32 for that 1 entry. So the product of these two matrices is this, just 32, okay? So a little complicated, and that was a rather simple example. You're going to see that this can get a little ugly. Okay, let me show you with the next one, and I'll try to help you with the organizational piece. So this is a 2 by 2 matrix. This is also a 2 by 2 matrix. So if the number of columns here matches the number of rows here, if those two things are equal, looks like a face, huh? If these two are equal, then we're good to go with multiplication. And when we multiply, our answer, our product, is going to contain the number of rows here and columns here. So this is going to show us the size for our answer, okay? Now here, our answer is going to be a 2 by 2 matrix. So a 2 by 2 matrix has 4 entries. And just to help you, again, organizationally, we've got 4 entries in this matrix. So basically what we saw happening in that first example, we're going to have to do 4 times here. And so it's like, what's going to go with what, right? Well, if you look in this answer, remember, rows by columns when we're naming a matrix. If we look at this answer, this product we're looking for, this is row 1, column 1 of the answer, which means to find what goes there, we're going to use row 1 and column 1. So if I use row 1 and column 1, I'm multiplying 2 and 1 and 6 and 7. So 2 times 1 plus the 6 times 7. Okay, I'm going to try that again. Let me erase some of this so I don't get too many circles in my problem. Okay, so looking at this part of the answer, this is still row 1, but now I'm in column 2 of the answer. So now to get that spot, that entry, I'm going to use row 1 and column 2. So it's 2 times negative 5 and 6 times 9. So 2 times negative 5 plus 6 times 9. Okay, let me do that again. So now here, I've moved to row 2 of the answer, but I'm back to column 1. So if that's row 2, column 1 of the answer, I'm going to use row 2, column 1 to get it. So 3 times 1 and negative 4 times 7. 3 times 1 plus a negative 4 times 7. And then lastly, our last entry, this is row 2 of the answer, column 2 of the answer, which tells me to use row 2, column 2 to get it. So 3 times negative 5 and negative 4 times 9. All right, now if we find all those products and sums, we're going to get our final answer here. So we have 2 times 1 is 2, 6 times 7 is 42, 2 plus the 42 gives me 44 here. And then I have, let's see, negative 10, and this is 54, so 54 minus the 10 gives me 44 again. And then we've got, let's see, this is 3, and this is negative 28. 3 minus 28 is going to be a negative 25 in that spot. And then lastly, running out of good color options here. Let's go black. So this is going to be a negative 15, and then negative 4 times 9 would be negative 36. So that's going to give us a negative 51 altogether. And there we have it. Simple, right? No, not exactly simple, but if you try to organize your work, I think that it's manageable. Okay, let me get rid of some of this. Okay, so let's try this again. Now again, I mentioned this earlier, how 6 and 7 have the same two matrices, but the order of these matrices matters. So the order in which we multiply matters. If we're looking at number 6, this is a 2 by 2 matrix, 2 rows, 2 columns, and this is a 3 by 2 matrix. It's got 3 rows, 2 columns. So the number of columns in the first has to equal the number of rows in the second, and since these, let me try to be consistent here, make sure that these all are aligning with what I did before. So if these two numbers are not equal, then it is not possible to multiply these. And just think about how we were kind of managing before. If I wanted to take this first row and multiply by this first column, 2 corresponds with 3 and 6 corresponds with 4, but there isn't anything to correspond with that entry. So even if you attempted to multiply these, you would see some issues with things not corresponding. So the number of columns in the first does not equal the number of rows in the second, which means this is not possible. It is not possible to multiply these two matrices. Now, same problem here, but rearranging these, again, this is a 3-row, 2-column matrix. This is a 2-row and 2-column matrix. Because they're rearranged now, the number of columns here and the number of rows here is equal, which means now we can multiply. And our product is going to contain the number of rows here and the number of columns here. So these two are going to show us the size or dimensions for our product for our answer. So our answer is going to contain a 3 by 2 matrix. 3 by 2, 3 rows. I did not make this a proper size. 3 rows, 2 columns. So 3 rows, 2 columns. 1, 2, 3 rows, 2 columns. Okay, so we've got 6 entries to go into this matrix. And again, use the location of the entry to determine what you're using to multiply to actually find that entry. So this would be row 1, column 1 of the answer, which tells me to use row 1 and column 1 to get it. So I'm multiplying 3 and 2 and 7 and 3. So 3 times 2 plus 7 times 3. I guess I could make this bigger, right? This is now row 1, column 2 of the answer. So let me back up here. I'm going to use row 1, column 2. So I'm multiplying 3 and 6 and negative 7, or 7 and negative 4. So 3 times 6 plus 7 times negative 4. Let me give myself a little more space over here. Okay, so this is, now we've moved to row 2, back to column 1. If I go here and use row 2 and column 1 4 times 2 and 1 times 3 is going to get us that entry. 4 times 2 plus 1 times 3. This is still row 2, but now column 2. So I'm going to use row 2, column 2. So 4 times 6 and 1 times negative 4. 4 times 6 and 1 times negative 4. Okay, we're getting there. And so now we have, this is row 3, back to column 1. So I'm going to use row 3, column 1. So 6 times 2, negative 2 times 3. 6 times 2 plus negative 2 times 3. And then lastly, still in row 3, but now we're in column 2. Row 3, oops, eraser. Okay, row 3, column 2. So 6 times 6 and negative 2 times negative 4. 6 times 6 and negative 2 times negative 4. Okay? So if you wanted to try to do all that in your head, I mean, you're welcome to. It's not possible for me. So I like to write out all those entries, put all the work out there, and now I can do some pretty simple math to figure out what our final matrix is supposed to look like. So we have here, let's see, 6 and 21, which is going to give us a 27. Here we have 18 minus 28, so a negative 10. This is going to be 8 and 3, which makes 11. This is 24 minus 4, so 20. And then we have 12 minus 6, so 6. And then this is 36, and then we have a positive 8 here, so 44 in that last entry. And there it is. Okay? So I've got one here for you to try. If you want to pause the video and give it a shot, not a bad idea. Otherwise, I'm going to work through it, and feel free to just work along with me as well. So this is clearly going to work. This is a 2 by 2 matrix, again a 2 by 2 matrix, and since these numbers are equal, then, that was a fail, since these numbers are equal, then we'll be able to multiply, and our product is going to be shown by the number of rows and columns, so it's going to be a 2 by 2. So a 2 by 2 answer, 2 rows, 2 columns, so that was pretty bad. So 4 entries. This is row 1, column 1. This is row 1, column 2. This is row 2, column 1. And this is row 2, column 2 of the answer. So for row 1, column 1. Row 1, column 1. It's going to be 1 times 2 plus negative 5 times 3. For row 1, column 2. Row 1, let me just so you can see it. Row 1, column 2. Row 1, column 2 is going to be 1 times 6 and negative 5 times negative 4. And now I'm going to move to the next row. Row 2, column 1 would be row 2, column 1 here. 7 times 2 and 9 times 3. And then lastly, almost there, bear with my edits here, row 2, column 2, right here, right here. So 7 times 6 and 9 times a negative 4. That was the hard part. And now I just need to do a little bit of basic math. So we have 2 and negative 15, which gives us a negative 13 in this entry. And then here we've got, didn't need to change color, 6 and then a positive 20. So 26 for that entry. Why am I doing these things? Okay, 2 and 7 makes 14 here. 9 and 3 is 27 here. 14 and 27 gives us 41 for that entry. And then 7 and 6 is 42. 9 and negative 4 makes a negative 36. So 42 minus 6 gives us 6 for that last entry. And there it is. Okay? So it's a manageable process. If you try to organize your work, I think that's going to be a little more helpful for you. And I really wish this was something that Desmos could do. They're actually beta testing a matrix calculator. If you want to Google Desmos or matrices on Desmos, you might be able to find something that pops up to help you. And if you're using a TI or a Casio graphing calculator, there is a way to do this multiplication with matrices in your graphing calculators. Unfortunately, I don't have those to be able to show you. If you aren't sure how to do it, you can look it up in your manual, look it up on Google. I'm sure you can find another video to help you with your calculator. So this is something that can be done with a graphing calculator, and I think, like I said, Desmos is beta testing a matrix calculator if you want to try to Google that. Otherwise, the work by hand is manageable, okay? But you're going to have to find the option that works best for you, all right? If you have any questions,